I'm very happy to be here. I have one PhD student who now graduated from this journey program, and I was very happy to work with him. And so today, and in the following lectures, I'm going to talk about emergent phenomena in quantum matter. So we know what matter is, right? In a piece of material, there are lots of electrons and atoms, 10 to the 23, for example. And practically, it's like infinitely many degrees freedom. That's matter. And we want to understand the behavior of those systems when they obey quantum mechanics. Okay, that's quantum matter. And emergent phenomena refers to behavior of those many degrees freedom that arise only in the limit that number of particles is infinite. Okay, you don't see such behavior in finite system, but only when the system size become infinite, you see something new that you don't expect to see when you have only few degrees freedom. Okay, so that's emergent phenomena. Okay, and there are different ways to talk about emergent phenomena. Really, the emergent phenomena that there are many different types of emergent phenomena, but in this lecture, we are going to focus on a particular model, simple model, called quantum rotor model, and we are going to study what kind of collective emergent phenomena can arise in this particular model. However, what I'm going to talk about later in the lecture really doesn't depend on this particular model. Here we are using just this as a way to introduce this phenomena, but what kind of phenomena can emerge does not depend on specific Hamiltonian. Okay, and then maybe later today or in the second lecture, we are going to introduce path integral representation. This is probably some of you already have read the reading material, but I'm going to introduce this because it's a very nice way of understanding quantum mechanical system. And then using this language, we are going to study different types of phases or collective behavior that can emerge from this model. Okay, so first is one of the trivial state called insulating state, and we will talk about what is called spontaneous symmetry breaking and topological order, and if time permits, we will talk a little bit about quantum criticality. Okay, so it's okay if you don't understand any words here. So the goal is to dissect these words in this plan. Okay, and please feel free to interrupt anytime if you have a question during the lecture. Okay, so let's start with the model. Let's start with before we think about 10 to the 23 degrees freedom, let's start with one rotor. So rotor is a particle living on a ring. Imagine you have a ring, and there's a particle moving on the ring. Okay, so the position of the particle is characterized by angle variable theta. Of course, it's a ring, so it's periodic variable with 2 pi periodicity. And in classical mechanics, we know that in order to specify a state of a particle, you need to know position. In this case, the angle is the position where the particle is. And then you also need to know the velocity or momentum. Okay, but here is angular degrees freedom, so instead of momentum, we are going to use angular momentum. But angular momentum just specifies how fast it is moving. Okay, so let's call that p theta. So this is position, and this angular momentum. But in quantum mechanics, we know that we cannot simultaneously specify both position and momentum because of the uncertainty principle, right? And these two obey the this commutation relation. Probably you have learned the similar commutation relation for a particle moving on a line. Here we just replace that with angle and angular momentum. Okay. Now, for our purpose, it is actually simpler to use a rescaled angular momentum variable. So instead of using P of theta, from now on, I'm going to use, by the way, in quantum mechanics, these are operators, right? So let's use hat. And we are going to use this new operator, which is scaled by h bar, okay, such that the commutation relation between n and theta is just minus I, okay? Okay. The reason why this is more convenient is due to the fact that, you know, if you consider a wave function of this rotor, then because of the periodicity, the wave function has to be single valued as theta changes by 2 pi, right? So therefore, if you represent this in terms of the Fourier mode, you can have only integer m here in order for the wave function to come back to itself when theta change by 2 pi, right? So here, and then in general, you can have some different coefficient that represent the weight for different mode, okay? And then in the position basis or in the angular basis, this angular momentum operator n that satisfies this commutation relation is simply derivative with respect to theta, okay? And you can see because the wave function is periodic with 2 pi, eigenvalue of this angular momentum operator has to be integer, right? So if you apply this operator to any of these basis state, you get eigenvalue m, where m is integer, okay? So that's why this is convenient. This is a convenient normalization that we are going to use. Okay, so you can choose, as in quantum mechanics, you can choose your basis state to be the eigenstate of either angular variable or angular momentum variable as usual, right? So if you want to find a state that has a definite position in the angular space, for example, you can have a wave function that is localized at angle theta 0. It will be some delta function, wave function like this, right? And then all set of wave function of this form for different theta 0 form a complete basis. Any wave function can be written as a linear proportion of these bases. Alternatively, we can use the eigenstate of the angular momentum operator as our basis, right? So for example, eigenstate whose angular momentum m, whose angular momentum is m, is just up to normalization. This is the eigenstate, okay? And again, alternatively, the set of these states form a complete basis. In other words, any wave function can be written as a linear proportion of this eigenstate of the angular momentum. Okay, this is the okay. So And then this operator measures how fast this rotor is rotating. Okay, that's the angular momentum. But also, this operator has an interesting role, which is that this operator actually is an operator that generates the translation in the angular space. So let me explain what that means. So suppose I start with some, suppose I start from some wave function, any wave function, okay? Say this wave function is peaked somewhere. It's defined, say, between 0 and 2 pi, and it is peaked somewhere here, okay? So this is my initial wave function. And suppose I consider a new wave function, psi prime, which is obtained by translating this old wave function by some angle delta in the angular space. You just rotate your wave packet here by angle delta. You can imagine doing that. So then initially it was peaked, so say at this angle theta 0, but then after translating by delta, this wave function is peaked at theta 0 plus delta, okay? So this is my new wave function, okay? And if this is normalized, this is also normalized wave function, okay? And one can imagine there must exist some unitary operator that maps this state into this state, okay? Let's figure that out, what that operator is. So this is my new wave function. It's related to my old wave function by translation with angle delta. Okay, so therefore, this new wave function is nothing but this. Okay, if I shift my argument by delta, this is my new wave function. Okay. Now I can tailor expand this as usual. Right? So I can tailor expand this around the delta equals 0. And then you can view this differential operator, this derivative as an operator that acts on this wave function. Okay? And then you can view this operator as an exponential of derivative operator acting on this wave function, right? And you know this derivative operator is nothing but the angular momentum operator up to this minus I. So I can write this operator as e to the minus I delta n acting on this wave function. So here the point is that the wave function that you obtained after translation by angle delta can be obtained by applying angular momentum operator in some way by exponentiating the angular momentum operator and apply to the original wave function. Okay? So this is a unitary operator because this n, physical observable, is a Hermitian operator, right? So this eigenvalue of this is e to the minus I times some real number. So norm of this operator is 1. So therefore, this preserves the norm of the wave function. So unitary operator, and this is a Hermitian operator. And we say this operator, in words, we say this operator generate the translation. Okay, that's a statement. Okay, so angular momentum, this n operator measures the speed, angular speed, but also it acts as a generator of translation in the angular space, in this sense. Okay. So let's just say here, N generate angular translation. Okay. Okay, so this set of translation, now you can consider different translation operator for different choices of delta. Okay, and if you collect all those operators, there are infinitely many of them because this delta can vary continuously, right? And then this set of unitary operators actually form a group. Okay, so this set of translation operator for all delta between 0 and 2 pi, for example, this form a group. What is group? Group includes identity operator. So if you choose delta equals 0, then you don't do anything, right? That's the identity. Then if you apply two translation back to back, the net result is equivalent to one translation with a new angle, which is given by sum of the two angles, right? And then also you can translate by delta, and then in here you can translate by minus delta or 2 pi minus delta, which brings the state back to the original state. So there exists an inverse. Okay, so in that sense, this form a group, and also it's a periodic between group elements at angle 0 and 2 pi is equivalent, and this particular group is called U1 group. Okay. So we say N is the generator of U1 transformation. So that's how we say it. Okay. And in this lecture, we are going to consider a model that satisfies particular property. So that property that I'm going to write is this property. So we are going to consider Hamiltonians which commute with the angular momentum operator. Okay? So if this happens, then we say the Hamiltonian is invariant under the U1 group. Okay? So, but that's just word. So let's consider what this implies. So if, as you have learned from quantum mechanics, if two operators commute, right? Then there are many nice properties. So one of them is that if I have some initial state, psi of theta, and if I know the energy expectation value of this state, okay? So energy expectation value is given by this, right? This is the energy of my state psi. Then you may wonder, what is the energy of this new state that I obtained by translating? Okay? So that energy is this. Okay? And then what you can show is that if Hamiltonian commute with the angular momentum operator, then you can show that this is same as this. In other words, energy doesn't change upon translating in the angular space. Okay, how many of you already know that this is true? Okay, I'm too elementary here. Okay, good. So if this is not familiar to some of you, I encourage you to prove this statement. Okay. Also, another property is that if I measure the expectation value of angular momentum operator at, say, time t equals 0. Suppose I have some initial wave function at time t equals 0, and I measure the expectation value of the angular momentum at time t equals 0. Okay? And then you can also look at the expectation value for a state at later time, where this psi of t is obtained from this initial state by solving the usual Schrödinger equation, right? And then you can ask, what is the expectation value of this angular momentum operator for a later state? Okay? And another thing that you can show similarly is that if Hamiltonian commute with the angular momentum operator, this is same. In other words, angular momentum is conserved. It doesn't change in time. Okay? So if Hamiltonian satisfy this property, if it commutes with angular momentum operator, so then two key property is that energy doesn't change upon translating in the angular space. Also, the angular momentum doesn't change in time. If you time evolve your state with Hamiltonian, your time evolved state has the same angular momentum expectation value as your initial state. Okay? Okay, so for those who are not familiar with this statement, this is proving this is an exercise. Okay? But many of you already know, so that's good. So we are going to focus on the Hamiltonian that satisfy this quantity, this property, because this is the Hamiltonian for which the angular momentum is preserved in time. So there's some conservation law here when Hamiltonian satisfy this property. Okay. Not all Hamiltonians satisfy this property, but there are more interesting structure when there is some conservation law like this. So we are going to focus on these types of Hamiltonian, where angular momentum is conserved. And in words, when we say that, we say H has the U1 symmetry. So this is just in words. This it refers to this statement. Okay. So you can try to classify different Hamiltonian depending on the symmetry that the Hamiltonian has, right? Does this Hamiltonian has a U1 symmetry or not? Okay, so then there's a class of Hamiltonian that has a U1 symmetry. And there's a class of Hamiltonian that doesn't have U1 symmetry. So therefore, angular momentum is not conserved. And usually, Hamiltonians that have different symmetry exhibit qualitatively different behavior. Okay? So this is a property of Hamiltonian. And we can also talk about symmetry of state. Okay? For example, symmetry of state is determined by asking how my state changes upon applying this translation. Okay? So if the new state that I obtained by translation is same as initial state, okay? If my state doesn't change upon translation, then we say the state has the U1 symmetry. In other words, state doesn't change, right? So that's the statement of state. Okay? It has nothing to do with the Hamiltonian. Okay? So if psi prime of theta is same as psi, then we say psi has the U1 symmetry. obviously, if state changes upon translation, then we say state breaks the symmetry. In other words, upon translation, you obtain a different state than previous state. Okay? Okay. Can anyone think about a state that has the U1 symmetry? Sorry?
If it's constant.
Constant, yeah. If psi of theta is constant, then upon translation it remains constant, right? So therefore, that state has U1 symmetry. What are the examples of state that breaks the U1 symmetry? Any kind of wave function like this, right? If it is picked somewhere, upon translation it changes, right? Or any kind of sinusoidal wave function with a non-zero angular momentum, upon translation it picks up some phase, right? That also doesn't have the U1 symmetry. So here, it is important to differentiate the symmetry of Hamiltonian and symmetry of state. They are two different objects. Sometimes your Hamiltonian may have U1 symmetry, but eigenstate of the Hamiltonian may not have the symmetry. Sometimes both Hamiltonian and state have the symmetry. Okay? Okay, so let's try to consider Hamiltonian that preserve the U1 symmetry, where angular momentum is conserved. So what kind of Hamiltonian can we write down that satisfy this condition? Okay, can someone? Sorry? Free particle? Okay, so for free particle, what kind of term can we have in the Hamiltonian? P squared, so something like n squared, right? With some coefficient, let's say C2. And, this say energy increases quadratically with angular momentum, but in some cases, maybe there is a linear term, and maybe there's a cubic term. In general, in most generality, can we also have a theta-dependent term in the Hamiltonian? Well, first of all, theta is a periodic variable, and energy has to be single-valued when theta changes by 2 pi. So therefore, my Hamiltonian can depend on theta only through some sine or cosine sinusoidal function, right? For example, e to the I theta, e to the I n theta is probably a good basis. So my Hamiltonian, in principle, can have some, say, b of n. I can have this kind of term here, right? For hermitivity, you may have to make sure that b of n and b of minus n are complex conjugate to each other. Then this is Hermitian, right? Okay, so this is most general Hamiltonian that you can write for the rotor model. Now, in order to have the U1 symmetry, we want the Hamiltonian to be commuting with the angular momentum operator. So the term that I wrote here in the first line is okay for any coefficient C1, C2, C3, right? It's n, so n commutes with n, right? However, these terms do not commute with n because theta, angle, and angular momentum do not commute, right? So therefore, any of these terms for n not equals to 0 is not allowed if we have a U1 symmetry. Okay? Except for m equals 0, but that's just constant. But that's trivial. Okay? So if we have a U1 symmetry, this is not allowed. Actually, you can convince yourself that this operator, say e to the I theta, for example, is an operator that changes the angular momentum quantum number by 1. For example, in this basis, e to the I m theta is an eigenstate whose angular momentum is m, right? But now, if I multiply e to the I theta to this wave function, I get a new state whose wave function is e to the I m plus 1 theta, right? So therefore, this operator raises the angular momentum by 1. So it modifies the angular momentum. So not surprising that if you have such term in your Hamiltonian, angular momentum is not conserved, right? Under time evolution, Hamiltonian includes the term that raises the angular momentum. So therefore, this property would not be satisfied, right? Or if you have a minus sign that lowers the angular momentum. Okay, so sometimes we call this raising or lowering operator of angular momentum. Anyway, the point here is that if you have a U1 symmetry, this is the only term that you can have. Okay. Now, to simplify the problem a little bit more, we are going to impose one more symmetry. We are going to say our Hamiltonian also respect the time reversal symmetry. So when we say Hamiltonian has time reversal symmetry, it means the following. So you have an initial state and have certain energy. And then now you construct another state obtained by applying time reversal operator to the initial state. And what time reversal operator does to the state is to change the speed, change the angular momentum, right? So if you have a particle that is moving with angular momentum 1 like this, right? If you watch that movie backward, you will see particle moving in the clockwise direction with angular momentum -1, right? So therefore, time reversal operator maps, say, angular momentum 1 state into angular momentum -1 state and vice versa, right? So if you have a thing that is spinning this direction, the time reversal partner of that is same angular momentum magnitude but spinning in the opposite direction. Okay? So if I want to have a time reversal symmetry, I don't want to have odd powers of n because this would differentiate the energy of +1 and -1, right? Is it clear? So therefore, if I have in addition to the U1 symmetry, if I want to have a time reversal symmetry, this odd powers of n is not allowed. Okay, so then I'm left with quadratic term and quartic term and etc. Okay, so this is the most general Hamiltonian for single rotor that satisfy the U1 angular translation and time reversal symmetry. Okay. In principle, we can keep all those high order terms, but for what we are going to discuss later, it doesn't matter whether we have a quartic term or not. So from now on, we are going to focus on this n squared term only. Okay? But if you want, you can include the high order term and see how that affects what we are going to discuss later. Okay? So let's now consider that simple Hamiltonian that we know how to solve exactly. Of course, it's a free Hamiltonian. So n squared. So I just put some coefficient here to, and I choose that to be u/4. I mean, it's just a convention. Okay, just use some fixed number. Okay, you can view this as inertia of angular momentum here. So now, of course, this is a free Hamiltonian, right? It's like only p squared term in the Hamiltonian. And we know the eigenstate is just the eigenstate of the angular momentum, right? So these are the eigenstate. E to the I n theta, they are the eigenstate, right? Where n is integer here. And so let's write this. Yeah, if you want to normalize that, you have to divide by this normalization. And the energy of this eigenstate is simply u over 4 m squared, right? So that's the spectrum. So the lowest energy state is n equals 0. So there is a angular momentum 0 state has the lowest energy. Here I'm choosing u to be positive. Makes sense, the energy will increase as particle moves faster. That's why we choose u to be positive. And then in the first excited state, n can be either 1 or minus 1. And the first excited state is doubly degenerate, right? So there's a m equal 1 here, and there's a m equal minus 1. And then m equal 2 and minus 2, they have a higher energy. Actually, it increases like 4 times like this, and so on, right? So this is the full spectrum. And in this case, if you look at the ground state, okay, so why do we care about the ground state? Because if you are at low temperature, okay, then the probability to have this excited state will be suppressed. So you will mostly see the contribution from the ground state. Okay? And then this ground state has a 0 angular momentum. And then, you know, in this case, the ground state has the U1 symmetry, right? It doesn't break the symmetry, right? Because it's constant, as we mentioned earlier. So in this trivial example, both Hamiltonian and states have the U1 symmetry, unbroken U1 symmetry. Okay, any questions so far? Okay, so this is too trivial. Now, let's consider adding more rotors and make rotors interact with each other. So we are going to consider a lattice of rotors. Okay. So far we just talked about single rotor, but suppose I have some lattice. Here I'm drawing 2-dimensional lattice, but it doesn't have to be 2-dimensional. And here I'm drawing, say, 2-dimensional square lattice, but the specific form of the lattice structure is not important. This is just an example. Okay. And imagine at every side, there's one rotor here. Okay? So there's one quantum mechanical particle that can rotate at each side. Okay? So then, here at side I, this rotor state is characterized by angle of that side, theta I. Okay? Then I also have a corresponding conjugate momentum, angular momentum operator at that side I. Okay. And for simplicity, let's say that my system has a linear size L, and the dimension, space dimension, I will denote as a D. This is space dimension. And also, this is not crucial, but let's consider a periodic boundary condition where this is identified with this, and this is identified with this. So in the 2-dimensional case, this is a torus. Again, this is not essential, but it makes math easier for later discussion. Okay, now, in principle, you can have U1 symmetry for every site. You may consider a model where the angular momentum is conserved for every site. But this is too restrictive, because then only term that you can have is just sum over angular momentum operator like this, right? This kind of term will commute with angular momentum operator at each side, right? But then nothing interesting happens because these rotors don't talk to each other. And usually in real world, only the total angular momentum is conserved, not the individual angular momentum. So therefore, we are going to impose only one U1 symmetry. Namely, we are going to say that Hamiltonian commutes only with the total angular momentum operator. Okay, so N total is sum of angular momentum over all sides. Okay. So this is the net angular momentum, and we are going to consider those Hamiltonian that is invariant, that preserve only the total angular momentum. Okay, so now at each side, angular momentum doesn't have to be preserved, but as a whole, the net angular momentum should be preserved. Right? So just as a side note, so then my wave function in general is a many-body wave function. If I have say L to the D side here, right? So let's call that volume, but V just represents the total number of sides. And then my wave function has to be function of theta 1, theta 2, all the way to theta V, right? So this is my many-body wave function for V rotors, right? Question, under this, what kind of transformation does the total angular momentum generate? If I apply this is some unitary operator, right? Because this is a Hermitian operator. If I apply this operator to this many-body wave function, how does wave function change?
All the thetas become theta.
That's right. So all thetas will be shifted by same angle delta, right? Because n is sum of individual angular momentum, and if sum is in the exponent, this becomes product of individual rotation. So at each side, angle is rotated by delta, by same amount, right? And this kind of symmetry is called global symmetry. We rotate by same amount globally. Okay, so then we say this Hamiltonian has the global U1 symmetry. So we are going to consider those Hamiltonian that has the global U1 symmetry. Okay, now, what kind of term can we add in the Hamiltonian while preserving the global U1 symmetry? Previously, for single rotor, this is the only term that we can have. But we couldn't add this term without breaking the U1 symmetry because this will add angular momentum to the system, right?
Now we can have terms like that because each individual particle can have its angular momentum increase.
Yeah.
As long as other has its decrease.
Great. So the suggestion is you can increase the angular momentum, say, at side I by 1 at the expense of lowering the angular momentum by 1 at side J, right? This kind of term will satisfy this condition. You raise by 1 here at side I, but lower it by 1 here. So total angular momentum didn't change. From this perspective, this total angular momentum generates the global angular translation. But if you change the angle by same amount in theta I and theta j, they will cancel. So therefore, this kind of term would be invariant under the U1 symmetry. Okay, so let's consider this kind of thing. So it's like you have side I here and side J here. And if I initially have, say, angular momentum 1 here, and if I have angular momentum 0, after applying, 0 and 1 here, then after applying this, you lower the angular momentum by 1 here in side J and raise it here by 1 here, right? So that will make angular momentum to move from one side to the other side, right? For this reason, sometimes people call this hopping term. It's like some particle moving around. But what it describes is the kind of spread of the angular momentum from one location to another location in this context. Okay? And in principle, this can happen between any pairs of sites with certain strengths that may depend on pairs of sites. Okay? However, there's a very important principle in physics that is locality. Right? In other words, 2 degrees freedom cannot interact with each other when they are very far from each other. They can interact only when they are close to each other. I can influence my neighbor, but it's very hard for me to influence someone in Canada right now. Okay? So that's the locality. So if you want to have a local theory, then this Tij cannot be too long-ranged. So from now on, we are going to focus on the case where rotors interact only with its immediate neighbors. Okay? So we are going to only consider the case where there are only nearest neighbor hopping. Again, this is not essential. You could include next nearest neighbor hopping and next nearest neighbor hopping, but these are kind of not important. Okay, so for the purpose of, for now, we are just going to consider simplest theory that exhibits some interesting emergent phenomena. But important point is that those emergent phenomena does not depend on details of this Hamiltonian. Therefore, sometimes it's enough to consider simplest one. So we are going to consider the case where this Ij pair runs only nearest neighbor. And then we are going to consider the case where for all nearest neighbor, they have the same strength of the hopping. Okay? This hopping strength does not depend on between this neighbor and this neighbor or this neighbor. They are same. Okay? With some strength T here. So U and T are parameters of the theory. So this is the Hamiltonian that we are going to consider. Yeah. So the goal in this mini course is to understand the ground state that arises from this Hamiltonian. Okay? For different choices of this T and U. Okay? Especially in the limit that number of rotors is very, very large. What kind of new phenomena do we see in the limit that V is infinite, that we don't expect to see when it is finite? Okay, that's the goal of this course. Okay, any question about this rotor model? Okay.
What commutation relations does this beta to y and j satisfy?
Okay, what do you think they will?
Canonical.
Yeah, so at different sites, they don't care. So of course, theta always commute. and NN also always commute. And then N and theta have a non-trivial commutator only when they are the same side, because when they are different side, we are talking about different degrees freedom. So it doesn't. I can specify the angle of this rotor and angular momentum of this rotor simultaneously, no problem. Right? Yeah.
Well, we know particles can get entangled, and that leads to non-local relationships between them.
Very good question. So, indeed, the state doesn't have to be local in the sense that the state doesn't have to have only, okay, you mentioned entanglement. So roughly speaking, entanglement is the following. If you look at the ground state, okay, in the limit that u is much, much larger than t, so we can largely ignore this term, then ground state will be basically every side has angular momentum 0, 0, right? So very trivial state, okay? And then when you turn a little bit of t, then what it does is that you create like angular momentum 1 and minus 1 among the nearest neighbor, right? So starting from very trivial vacuum where there's every side has a, okay, now I'm drawing this in the one-dimensional way. So you start from state where all side has a 0 angular momentum. When this is the exact ground state when u is 0, but now t is 0, then now you turn a little bit of t, then this is no longer an exact ground state because this t term here will create, say, angular momentum 1 and minus 1 like this, right? And then here as well, somewhere here, minus 1 and 1, something like this, right? So your ground state will be linear superposition of different state with the different pairs of 1 and minus 1 or n and in general minus n angular momentum, right? And then you can ask how far this pair can be separated, okay? And this doesn't have to be local. This doesn't have to be bound within a finite distance necessarily. Although Hamiltonian is local, your state can have non-local feature, for example. The typical separation between these kind of, I will use the term particle and antiparticle because they behave like it, because when they meet, they pair annihilate. And this pair can be created out of nothing, out of vacuum. So they behave like particle and antiparticle. And then you can ask, what is the typical size of the particle-antiparticle pair? There's some length scale you can define for that, right? And that length scale doesn't have to be finite. In that sense, your state doesn't have to be local in that sense, although your Hamiltonian is local. That's a very good question. Okay, so that's also actually one way of characterizing what state, what phase you are in. Okay, that's a very good way of characterizing different emergent phenomena. Okay. Yeah.
Yeah, I have another question.
Sure.
Why are we only considering generations of one angular momentum, not more?
Oh, you can have more conserved quantity. You can certainly have, but
Why don't we have like m of the exponential, so that we have m and minus m angular momentum being created?
oh, okay. So here, why we just consider unit angular momentum creation here? Yeah, okay. In principle, yes, you're right. You can have this kind of term. You can have this kind of term as well. But again, this doesn't change the essential feature of emergent phenomena. You may have to choose different values of t and u to see, say, topological ordered state or symmetry breaking. But the qualitative feature of the state doesn't change, doesn't depend. That's why we choose the simplest minimalistic model. Yeah. But they are allowed. Certainly in real experiment, they are present.
So we should, in principle, include all
Yes.
possible values on the explanation.
Yeah, that's right. And also allow some local but finite range hopping as well. Okay, so this is the goal, to understand to understand the ground state of this Hamiltonian and try to understand what kind of emergent phenomena we can obtain. Okay. Unlike single rotor, unfortunately, we cannot obtain exact ground state for this Hamiltonian, even without this higher angular momentum term. Even for this minimalistic, simple Hamiltonian, we don't know how to calculate the exact ground state. Okay? However, that doesn't stop us from understanding some feature of the ground state. And formally, one way of obtaining, okay, so first of all, the difficulty lies in the fact that this first term, what I call U term, and this what I call T term, the T term is the hopping term that try to spread angular momentum in space. And U term is the term that penalizes the state with a large angular momentum, right? And these two do not commute with each other. If I want to find the ground state by minimizing U term, by having low angular momentum here, well-defined angular momentum here, then T term is not happy in the sense that the energy of T term become large. Conversely, if you want to minimize the energy for the T term, then you have to have a well-defined phase. A well-defined phase means large uncertainty in momentum. So therefore, you have to pay a lot of energy for the U term. So that's why it is hard to find the exact ground state. They compete. Okay. So, however, there's a way to formally write down the ground state of such generally interacting Hamiltonian, which is the following. First, you guess your wave function, your ground state wave function. So my guess, I'm going to write as a psi s. This s stands for seed. This is a seed state. Okay, I'm going to write just like psi of theta, but what this really means is a set of variable, right? From 1 to v. Okay, so I start from some seed state. This is my best guess. Then we can try to improve it. And one way to improve the ground state is by cooling the state. So by cooling, I mean the following. We can apply this kind of operator where T is sometimes called imaginary time. I mean, that name came from the fact that if you solve the Schrödinger equation, formally this is the solution of the time-dependent Schrödinger equation, right? So that here you evolve your initial state by time t, then this is the operator that evolve along the real time. And this operator is obtained if you take time to be imaginary, minus I tau, then you obtain this, right? So for that reason, you call that imaginary time evolution. But this is just a nice way to suppress the contribution of excited state in your seed state. So in your poor guess, probably you have some ground state component as well, but there are some excited state component as well, right? So in general, your seed state will be some linear proportion of, say, m I use for angular momentum. So let's use A. Okay, it will be, so this refers to eighth exact ground state, eighth exact eigenstate of the Hamiltonian, right? But then, if you apply this operator to this seed state, then each component is suppressed by exponential of energy of the state, right? Because this is the ground state of Hamiltonian with energy E of A, right? So therefore, if I take the large T limit, then all the contribution of the excited state will become vanish zero compared to the weight of the ground state, right? So you can write this as there will be some overall suppression of the ground state, but relative to that, there's some, in general, you can have more than one ground state. So let's say A prime represent a set of ground state here. So you will have a contribution from that ground state, but everything else will be suppressed by or other states that are not ground state will be suppressed by this exponential factor, right? So in the limit that t become very, very large, this contribution goes to zero. So if you can somehow compute this imaginary time evolution from your seed state, then you will get up to some normalization, you can get the ground state. Okay? Yes?
Why is there another summation with A prime?
Oh, okay. So this A prime, in general, you can have more than one ground state. So this A prime label different ground states. In the simple example here, for one rotor, we have a unique ground state. But we will see in some cases you can have more than one ground states. And then if you have a multiple ground state, they have the same energy. So that's the summation. And then what survives will depend on the weight of your seed state. Okay? So in general, this will be one of the ground states. So, and then I will call that ground state. In general, it depends on the seed state. So I will write G as the ground state obtained by cooling seed state S. Okay? Okay, so this is the how one might try to compute your ground state. Okay. Okay. Now we are going to try to compute this imaginary time evolution using the path integration formalism. Okay. Okay. Okay, so let's write my Hamiltonian as a sum of t term and sum of u term, where t term describes the hopping of angular momentum between nearest neighbor sides, and U term is the kinetic energy of each rotor. Okay, and let's try to compute this using this Hamiltonian. Okay. Again, the difficulty is that I have two terms in the Hamiltonian that do not commute. Okay, so that makes it difficult to compute this. If it was only T term, that will be easy because T term has only diagonal elements in the angle basis, in the position basis, right? But U term is a diagonal in the angular momentum basis, not in the angle basis. So T term and U term prefers different basis in a sense. Okay, that's why it is hard to compute this. And path integration is one nice way of kind of compromise these two, and it goes the following way. So first, I'm going to break this time evolution from 0 to, say, capital T, imaginary time, into many small steps. Okay, so I'm going to break that one big time evolution into many infinitesimally small steps where I have T over epsilon of them, and I'm going to make epsilon really small at the expense of making this very large. I can do that, and when epsilon is very small, it's infinitesimally small time evolution. So what I can do is that if I have a T term and U term to the leading order in epsilon, in the limit that epsilon is very small, because what really what enters in this evolution is epsilon times T and epsilon times U. So anything that is non-commuting is order of epsilon square, because non-commuting term arises only when I have both T and U term, right? So therefore, to the linear order in epsilon, I can write this as like this, to the linear order in epsilon. So error here is order of epsilon square. And as I take epsilon goes to 0 limit, this will be much smaller than this leading order term. You can check this by just tail expanding both sides, right? Yeah, maybe this is a good exercise. Tail expand both sides and check that these two agree to the linear order in epsilon. Okay. Then what I can do is that I can first apply the T term to my seed wave function. That I know how to do it because, say, okay, so let's compute this. U. Okay, so this HU is a function of angular momentum operator n, and HT is a function of this angle operator theta, right? Now goal is to compute this when it acts on my seed state here, okay? But the first part is easy now because this is each, okay, this is just number in the angle basis because this operator is diagonal in the angle basis, right? So therefore, I can write this as a e to the minus HU and e to the minus HT. Now this theta hat, the operator, takes the eigenvalue for each theta. This takes the eigenvalue of this theta here, right? So this becomes just a classical variable theta here of my seed state. Okay. Is this okay? Yeah. So if you have a X operator and acting on some state, and this just acts as a number here in the position basis, right? So position operator just acts as a number in the position basis. The same way, this operator acts as a number in this angle basis. Okay, so I have done this part of evolution, which was easy. Okay, but now this is hard because n acts like a number is diagonal in the angular momentum basis, not in the angle basis. Now this is a wave function written in the angle basis, right? So what I'm going to do is to expand this wave function here as a linear superposition of angular momentum eigenstate. Okay, so I'm going to write this as a sum over m e to the I m theta of some psi m. This is just number. Okay. Where this is nothing but the Fourier mode of this wave function, m Fourier mode of this function, right? So you can compute psi of m just from the inverse transformation of this wave function, e to the minus im theta prime of this function here. So e to the minus epsilon ht theta prime psi s theta prime. Okay. Now this is useful because this is an eigenstate of angular momentum operator with the eigenvalue m, right? So now when this angular momentum operator acts, okay. Sorry, I was sloppy here. So by this mean, so there are many sides. So there are angular momentum for each side. So e to the I m I theta I, and then psi m. Okay. So here this is a many-body wave function. There are v rotors, right? And I'm decomposing as a linear superposition of angular momentum eigenstate where each side has angular momentum mi. Okay, then psi m for is inverse Fourier transformation of this many-body wave function, which is given by so product of all sides I and then I like this. Now, this object can continue when this angular momentum operator, say if ith angular momentum operator acts on this wave function, it immediately takes the eigenvalue mi. If I have a jth angular momentum operator, it takes mj, right? Is this clear? Right. So therefore, it becomes e to the minus epsilon h u. Now, every ni here is just become m. I will just drop the subindex I, but this means that every ni become this eigenvalue mi. And then here I have a sum over mi. And then this weight is given by this, which is product of I Okay. So this is the sorry, I missed this factor, sorry. Times e to the okay. E to the minus epsilon. Okay, so this is the result of state that you obtain after applying one infinitesimal imaginary time evolution. Okay, so let me just rewrite it. It's sum over all possible angular momentum and sum over all possible angle, and then I have e to the I mi theta I minus theta sorry, this is supposed to be prime, sorry, prime minus epsilon hu mi plus ht theta prime psi prime.
Just a comment. I think maybe it would be a good point.
Yeah.
To finish this one step.
Yeah, I think this is a good point to stop. And tomorrow or maybe Wednesday we will continue to finish the path integral representation from here. Okay, so any question about up to this part? Yes.
Yes. Which is the I index that depends in the mi that we are choosing?
Oh, sorry. This repeated in this. These are summed over or side.
No, but in the last part you are.
This index is all summed over.
Yes, but also the product. You're using I. So which I is from the product and which one is from the mi?
So this one represents d theta 1 to d theta v. So this is the product.
Okay, yeah.
And then this sum represents sum over m1, mv.
Okay, perfect. Yeah.
Yeah.
Thank you.
More questions? As Nathan said, this is probably the most important part.
So here, this theta is the variable for the wave function. This is fixed. And then theta prime is integrated over. Okay? And then m is also summed over. Then final answer is function of only theta, which gives the wave function after you apply this evolution.
I think in the first line you have a prime on m on the.
That
should not be there.
Yeah. M doesn't have prime here. Theta has prime. Yeah.
Questions? Let me get to the microphone.
Exactly what is the theta I? It's just the theta before? No, the line below.
Here?
Yeah.
Okay, so I think this, okay, so now the point is that this is a many-body wave function, right? Before applying the evolution. And then the goal is to find the wave function. So this is the new wave function. This is some new wave function, say theta tilde or psi tilde of theta. So this is my new wave function after evolving this, my seed wave function.
Yes.
Then you have to apply this operator, right?
Okay.
So now this theta is fixed. This is the argument of this wave, new wave function. So this theta is here. This is this.
Oh, okay.
This keeps track of how this wave function depends on theta here.
Okay.
Okay? And then this theta prime here is a dummy variable you integrate over. It came from computing the Fourier components and Fourier component of this, this wave function here.
Oh, okay. Thanks.
More questions?
So here, what we do is first apply the t term here. That just gives this new wave function, which is a function of theta, right? So let's keep track of how theta. So this is theta. So this is the external variable here, right? And after applying this t term, it is this theta here. This is just a new wave function of theta. It's a function of theta, right? And this is the Fourier component of this wave function. And this Fourier component is given by inverse Fourier transformation of what is in the box here. So this psi m here is given by inverse Fourier transformation of this box. The box is this guy here. Okay. So this is the mth Fourier component of this wave function here, where this theta prime is just a dummy variable here. Okay. Now we apply this second evolution by U-term to this state. And then when n acts on this angular momentum eigenstate, this n become m. Okay, that's how I get this thing here. And then I have e to the im I theta I. I still have this one. And then this contribution from energy m is this first term. Then what is written here is just this Fourier component, which is written as an integration of dummy variable theta prime here. That depends on only m here. Yeah. So at the end of the day, the whole thing, the theta dependence, external theta dependence is only here. M and theta prime are summed over.
Which kind of emergent phenomena do you expect to get in this model?
Sorry, I couldn't hear.
Which kind of emergent phenomena do you expect to get in this model?
Okay. So in this part, we are going to see the phenomena where, although the Hamiltonian has the U1, global U1 symmetry, the ground state doesn't have that symmetry. Okay, the ground state is not going to be invariant under angular rotation. So that's called spontaneous symmetry breaking. Symmetry is broken by state, but not by Hamiltonian, but by state. So that's why we call it spontaneous. So this is one of the phenomena. And then another phenomena is so-called topological order, where different ground state, you get multiple ground state, but they differ by some global aspect of the wave function. So we will get there later in the course.
I've also got a question. This is sort of reminiscing the Ising model of spin interaction, isn't it? Or am I missing something? Isn't this like similar to Ising model?
Where this model is more like sometimes called XY model, because this rotor can be viewed as a spin that can rotate in the plane that has both X and Y component. So Ising model would be the model where angle can be either only theta or pi. If you have only two possible choices, that will be Ising model. Ising model has a different symmetry. It has the so-called Z2 symmetry where you flip direction of spin. But here we have a U1 symmetry where energy is invariant under continuous rotation.
So it's like a continuous version.
That's right, yeah.
Okay.
Yeah, that's,
Any other questions? Are we Are we supposed to take a break now? Do you remember?
No, I think it's straight up.
No break?
Yeah.
Okay. So after this next session, of course, feel free to ask more questions to Sung-Sik, and let's thank Sung-Sik again.